All right, can you all hear me okay?
Yeah.
Okay, so we're back. We'll continue our discussion. And so what I want to do is go through this. I want to go through this problem where I want to calculate the currents in every loop, the current in this loop and this loop. I want to use Kirchhoff's laws. This is our first application of Kirchhoff's laws. And so I guess the first question is, how do I designate the currents? And really, it's kind of arbitrary how we designate the currents. So I'm going to say the following. I'm going to say, well, I'm going to start here and say at this junction, the current splits up this way and that way. Okay, and just to be consistent with my notes, I'm going to call this one I1, this one I2, and really this is the sum of I1 and I2. I can call it I, but this is I1 plus I2. I don't want to call it, and the reason why I don't want to call it I is because I just want to write it in terms of my independent variables. So I really have two currents here. I have I1 and I2. That's it. When you get to this point, I1 and I2 join together, and I have current I1 plus I2 here. Because of the fact that I have two independent currents, I only need two loops to solve this problem. In other words, I'm going to sum voltage drops on two of the three loops. I just got to make sure that the two loops are independent of each other. That's all. Oops. Okay. So in the figure, try to be consistent with my figure. These are the currents. And what I'm going to do first is choose this loop here, and I'm going to sum the voltage drops clockwise, and then I'm going to choose this loop here and sum the voltage drops clockwise. I can go clockwise or counterclockwise. It really doesn't matter. What I'm trying to do is really I'm calculating this. And I'm trying to calculate this. So I'm integrating in the direction of the electric field right now. So if this integral is positive, delta V is negative. If I integrate around the whole loop, I should make it R because I've been using R. I get 0. This is Kirchhoff's voltage law. But for each individual ones, I'm just using this. The integration gives me delta V. E is constant. Or, I'm sorry, E is uniform. Okay. Are we clear on that? So as I go this way, the current is going from right to left here, and I'm going to be summing right to left. So this is going to be a voltage drop. Okay, here the same thing. This is going to be a voltage drop in this loop. However, in this loop, because I'm going against the direction of the current, the electric field, then this is going to be a voltage gain. Okay, so let's start with the bottom loop. It doesn't matter where I start. I can start here, and I'm going to go clockwise. So as I go through the battery, I go from a lower potential to a higher potential. I have an increase in potential. My delta V is positive. Then I go through the resistor. The current is going this way through the resistor. The total current here is I1 plus I2 times the 0.1 ohms. That's the voltage drop.
You know it's a voltage drop just because it's a resistor, right?
Well, the reason why it's a drop is because I'm integrating in the same direction as the electric field. This dot product is positive.
Oh, and it's, yeah, okay.
Okay, so if this dot product is positive, I mean, if this integral is positive, I still have this minus sign out here, right?
Yeah.
I don't have to use this convention. I can say that going this way is positive, but I'm using that convention. There's different conventions that are used. Okay, I'm gonna stick to a particular convention.
Sure.
And it's just consistent with this.
Mm-hmm. Which is what we used before, so.
I get to this resistor. I'm summing in the same direction as the current, and so that's also going to be a voltage drop. And the current through is I2. And then I go from positive to negative, I go minus 12. And that's equal to 0. Let's do this top loop. I'm going to go clockwise in the top loop. I can start here. I go from negative to positive. I get a voltage gain. Now notice I'm summing this way, but the current is in the opposite direction. The current is in the direction of the electric field. So this dot product will be negative.
Which means it's positive.
This will be positive.
Okay.
And so I 0.01 I2, and I'm sorry I'm not putting the units in for the resistance. And then I go hit this resistor. The current to the resistor is I1.
And that's with the current, with the electric field.
So it'll be minus, right?
Yeah.
So I have two equations, and they're pretty much independent of each other. Let me rewrite them. 14 minus 12 is 2. Okay, so minus and then this one okay, so I have those two equations. Why don't I take the bottom one and multiply through by 11? Okay, I'm going to multiply the bottom one by 11. So 11 times 12 is 132. This gives me 13.2. And this gives me 0.11. And so now I'm going to add the equations.
Why did you multiply by 11? Just because of the 0.11?
Yeah, so I want to get rid of this.
Okay.
I didn't want to do substitution. I know people like doing substitution. But I want to do it this way. So these two cancel. And what am I left with? This is 134. And what does this come out to be? So I1 is 134 over 13.3. And that comes out to be 10.1 amps. It's always easy for me to make a mistake on the board, so just check my math. And then I2, how do I get I2? Well, I just go back into this equation.
Yeah, and you plug in I1.
Yeah. And you get I2 is 19.1 amps. You can do that on your calculator. So this is 10.1. This is 19.1. 19.1, yeah. And so the total current through here is over 30 amps. Okay, it's the sum of the two. And the voltage drop across A and F is the same as the voltage drop across B and E, is the same as the voltage drop across C and D, and you should check that. Are we okay with that?
Yeah.
Okay. So that's a simple application of the Kirchhoff's laws. So let's do one that's a little bit more complicated. So let me draw this circuit. And in the notes, I've done this problem 2 different ways. And I'm only going to go through one of them, and you can look at the other method. Okay? All right, so this is our familiar circuit. And so this power supply is 13 volts. And let me put in the values. This is 1 ohm. This is also 1 ohm. R sub C is, I can't see it on the screen. Hold on, look at my notes. 1 ohm. R sub D is 2 ohms. And this is 1 ohm. And so what I want to do is find all the currents. And this is going to involve some work. So I'm going to assume current's going to go this way, and it's going to split here into I1 and I2. So this is I1 plus I2. You can call it I, but I like calling it I1 plus I2 because I know that the sum of these two is equal to these two values. I'm sorry, the sum of these two is the current through here. Now what about when we get to this point? Well, this current I1 splits into these two.
So you could do like I1A and I1B or something, or I1E and I1C.
How about if I call this I3? And I call this I, isn't this going to be the difference between these two?
Oh yeah.
Right now I still have only 3 independent currents.
And then that means that from that other side is going to be plus the other two, right?
Yeah, I2 plus
plus
I3.
Yeah.
So I really have 3 independent currents, so that means I need 3 loops.
All right.
Once you get to this point, I think the problem gets a little bit easier. The rest of it is just making sure you don't make errors with minus signs. Okay. So now I got to choose loops. And I have a lot of loops to choose from. I got to be careful. I do not want to choose, this would be bad. This loop, and the diamond. And the reason why is I've never included a power supply. And the other thing is, if I do this loop, and the diamond is probably going to be the sum of those two loops. I won't have three independent equations.
Could you do including the 13 volt in all of them, where essentially it goes through the current for each loop?
Yeah, I do want to include this one.
Yeah.
So if I do this loop, and this loop, that's fine. I mean, or I can do this outer loop too, or this inner loop. I mean, it varies. But I just want to make sure my equations that I have are independent of each other. So let me show you the loops I've chosen. And just for fun, I'm going to go counterclockwise. That'll be loop 1. This will be loop 2. And then the outer one is loop 3. And I'm going to get 3 independent sets of equations. And then I can solve them. And because I've applied the current rule right away, I mean, I'm in good shape. In the old days, they would just have you write 3 equations, and then also apply the loop rule. You would actually have 4 equations and 4 unknowns, but we don't have to do this now because I already applied the current rule. That's why I like doing it this way. By the way, the method I'm using here is from a book called University Physics. By Young and Friedman. I just like the method they describe. It's not the one that's described in our textbook. I just like this one the best. Every book has their strengths and weaknesses, but they did a good job in doing Kirchhoff law problems. Okay. All right. So let's sum voltage drops. We'll start with loop 1. Okay. And let me do loop 1. I'm going to go this way. Let me start here and go that way. So let me go through I1. So I have I1 times 1 ohm. And this is going to be a drop because I'm summing in the direction of the current. So
it's negative.
Negative I1.
Then are you doing the across the way, the E or RE?
I'm sorry. Yeah, this is E, right?
You're doing the I3 one in the middle. You're going across the middle.
Yeah, I'm going to go across the middle. So that's also going to be a negative, right?
Yeah.
I didn't draw the arrow for I3. So minus I3. And then as I go through here, I'm going opposite. I'm summing opposite the direction of the current. Okay. That's 1. Let's do loop 2. Loop 2 is this one. So I can start at the power supply. 13 volts. And then I reach this resistor. And then I reach this other resistor, again, another voltage drop. So that's equation 2. And then the last one will be the outer one.
Why is it I3 minus I1? I thought it was I1 minus I3.
Oh, yeah, you're right. Sorry.
Okay.
I don't know why I did that.
You were testing me.
Okay. So loop 3, I go 13 volts. And then what about this one?
That's just I2. That's negative though. And the last one is also negative, but it's times 2.
Okay. So let me rewrite these. I'm going to rewrite this one as like that. This is minus 2I1. And this is plus I3. And then the bottom one is minus 3I2. And minus 2I3. Right, here's my 3 equations. So I have 3 equations and 3 unknowns to solve for. Right?
Yeah.
Okay. What if I add this one to this one?
Which one? The first one to the second one?
Yeah.
Then you can cancel out the I3.
Actually, no, not. Hold on a second. That would be bad if I did that. Let me multiply the top one by 2 and add it to the second one.
Okay.
What does that give me? I add them. And I'm sorry, I'm not putting the units in. I know I got to subtract them, right? 2.
Yeah, you'd have to subtract because to cancel out the I1.
Okay. It's so easy to make a mistake on these when you get to this point, especially when you're doing it on the board. Okay, so let me write the other equation underneath. So what am I going to do? I'm going to take the top one, multiply it by 2, and the bottom one, and multiply it by 3. Oops, wrong one. So that's going to give me (13 times 2 is 26). And then this one is going to be And now I'm going to subtract.
Yeah.
Hold on a second. I have a sign error somewhere.
No, I got that. I got what you got.
You got what I have?
Except wait. I only have one or two I2s on the top. Oh, wait. No. Oh, no. No, sorry, that was my bad. Now I have the same as what you have.
Somewhere there's a mistake. I gotta find my mistake.
Did you get something different in your notes?
Yeah, I do have something different in my notes.
Are your notes correct?
I have a sign error. One of these two signs is messed up. Hold on a second, sorry. Oh, actually, I don't have a mistake. You know what I did? In my notes, I solved for this one. I'm solving for this one.
Oh.
That's my mistake. So I'm actually correct. I was trying to, I'm supposed to solve for this one. Anyway, we'll solve for I2, that's fine. So this is 13I2 equals 65, right? No.
No, it's
yeah, 65.
So negative 13, right? Oh, no, because it's minus.
Because it's minus. So I2 is 5 amps. Okay. If you solve for I3, you plug this back in here.
You can also do it in this other equation, the negative 2i and I3.
Oh, this one? You want to put it here?
Yeah, just it seems like a simpler equation, so. Wait, no, sorry, that's not a T2.
Oh, that's a 1.
Or an I1.
Let's go back to this one.
Yeah.
Okay, so this is 20 minus 6I3. So I3 is minus 1 amps.
Yeah.
So what does the minus 1 tell me?
Then it's the reverse direction, right?
Yeah, so the minus I1 tells me I chose the direction incorrectly.
Yeah, which means, because that was against the flow, right?
Right. So that's all it tells me.
Yeah.
And so, let me see if I can get a different color here. So this is minus 1 amp. This is 5 amps. So the current's really going this way. So what is this current?
That one, we haven't solved for that one is 4.
4.
Yeah.
Okay.
We haven't solved for I1 yet.
So you got to solve for I1. So if you use this one, minus 2.
Or even just the top one. That top one.
This one?
where they're all in. Yeah,
Oh, this one right here.
yeah, where they're all individual stuff, which makes it -4, right?
Isn't it 6?
Oh, you're right. Yeah. Wait. Oh, yeah, it is.
And this is 7 amps, right?
Yeah.
So really, that's it then. Then the rest I can find the voltage drop just by multiplying, this times this gives me the voltage drop.
Yeah.
Once I got the currents, I have everything. And then, yeah, this current is going to be 6 plus 5. But it's easy to make math errors. Okay. Now, in your notes, I have a mathematical method you can use if you want. Have you had Math 33?
Yeah.
Okay, so you can use row reduction if you want. And so I do have some notes on it. I don't want to take time here to go through that, but I do have in your notes a way you can use row reduction to solve the problem.
Okay.
Okay, but otherwise, I mean, you can do this on an exam, because I'm only having you use a scientific calculator. I'm going to make sure that the equations aren't too complicated for you to solve. If I give you a complicated circuit, then I'm only going to have you set up the equations. Okay.
All right.
When you take engineering 17, you're going to be asked to punch the number. You'll actually be allowed to use an engineering calculator, and you can just punch the numbers in, and the calculator will give you an answer. I'm more interested in you setting it up, but if I give you a simple circuit, you should be able to solve it.
Yeah.
Okay. So yeah, I do have some notes on row reduction in your notes, so you can take a look at it. So I just want to quickly show you another way to designate the currents. And so what I'm going to do is make the slide bigger and go through it. So one of the things I can do is say, okay, well, what if I call that one current I1, the second current I2, I mean, I'll have those three like that. That one's I4, and that one's I5. I want to write everything in terms of I3, I4, and I5. Okay?
All right.
So then I1 is I3 plus I4, and I2 is I5 minus I3. So then I can write everything in terms of I3, I4, and I5. And then I can choose loops. And I can sum the voltage drops. I have it. You can go through this yourself.
Yeah.
Okay. So the only difference is I chose different current designations.
Yeah, you chose the bottom loop instead of the top.
Yeah, and you can go through then and solve the problem again, and you should get the same results, except that you'll get I3, I4, and I5.
Yeah.
If I have this in your notes, and so you can go through this and solve the problem. And I don't show you the solution there, but and on the screen, but in your notes, the entire solution's there.
All right.
Okay.
Where are the notes, by the way? Because I've tried to find them before and I don't.
I emailed them to you guys. You should have.
That's right.
If you didn't get an email, please let me know, because I can always send them again.
Okay.
All right, so what we're going to do next is actually go back and do a simpler circuit. at least a simple looking circuit. And it's just a circuit that includes basically a resistor and a capacitor.
And a switch, right?
And a switch. The switch is there, yeah, just turn to start the process going. And in reality, with a DC power supply, these circuits are very boring because once the capacitor is charged up, that's it. Current starts flowing, okay?
Yeah.
So it's more interesting if you have a voltage that changes, or maybe a switch that opens and closes. Okay. But we have signal generators that provide a voltage like this.
Is a switch kind of how a circuit breaker works?
Yeah, right. Basically, you open that switch and there's no current, right?
Yeah.
So when you have a circuit breaker, you know, the circuit breaker breaks the circuit. You have an open switch.
Yeah, makes sense. The name makes sense.
And we used to use fuses. So you go to the box outside or or in the basement of your house, and you would just screw in the fuse.
Oh yeah. I think I've seen those.
Everything with circuit breaker, you can just reset them, right?
Yeah.
If you blow a fuse, you got to go buy another fuse.
Yeah.
So I want to look at a circuit with a resistor and a capacitor. And these are good for timing. They have a lot of applications. If you have a real high voltage power supply, for example, like a 3,000 volt supply, and you shut it off, you don't want the voltage to go from 3,000 volts to zero. And so what happens is you have a RC circuit that allows the voltage to slowly go down to zero. You don't want big voltage changes. It's bad. So here's my capacitor, and here's my resistor. And I'll put the switch here. So when the switch is open, nothing happens. It's boring. But when I close the switch, what happens? Well, charge starts to build up on the capacitor. But the resistor opposes the flow of charge. And so the capacitor is not going to charge up right away. It's going to take time for the capacitor to charge up. What we want to know is how the capacitor charges up as a function of time. Can we derive an equation for the charge on the capacitor as a function of time? Or can we derive an equation for the voltage across the capacitor as a function of time? Or the current in my circuit as a function of time? That's what we want to look at. What's harder here is that this is neither a series or parallel circuit. I can't use those principles. However, I can use the loop rule.
What?
Kirchhoff's loop rule. I can use the loop rule.
Oh, the loop rule. I heard the Luke rule.
Or the voltage law.
Yeah.
So I'm going to apply that. You can always apply this, and the reason why, it's a general principle. Okay, so I went too fast. I guess some stuff is missing in my notes there. So let me apply the loop rule. I'm going to assume that the current is going to be like this. And I'm going to sum the voltage drops in the same direction. So I'm going to go this way. So let's say I start here. I have a voltage increase. Capacitor voltage drops. And then the voltage across the resistor drops. Well, for a capacitor, Q is C delta V. And so delta V sub C is Q over C. And of course, for the resistor, you know what it is. Okay, and you say, okay, where do I go from there? Well, how is I related to Q? The rate at which this capacitor charges up has to be equal to the rate at which charge flows through the resistor because they're in series. We know I is dq over dt, right? I is dq over dt.
Yeah.
So delta V and this delta V, I guess I should put a subscript, is our power supply voltage. So now what? Let me move this to the other side of the equation. And I get R dq dt is equal to delta V sub S minus Q over C.
Then do you divide by R? And
Let's
integrate,
okay.
or?
You want to divide by R?
Yeah. I mean, would that help? I mean, we can also just integrate now. I don't know if that's what you're trying to do, though.
That's my goal, but I gotta
Because
I
R
gotta
is
isolate the Q's, right? So basically what I gotta do is,
oh, right. You have to add. Wait.
let me multiply both sides by C.
Yeah, yeah, that works.
So what I'm gonna do is bring these two terms here and this term below. So I'm gonna get the following. Let me erase my board. So now I'm in a position to integrate because I've separated variables, right?
Yeah.
Okay. Let's see. How can I do this easily? When I integrate this, I'm going to get, what am I going to get when I integrate this?
Could you set it up as two different integrals?
Well, I have an integral
Like
here.
dq over. Oh no, I was thinking of. I was trying to do the thing you can do with numerators. But.
Well, when I integrate this, I'm going to get, aren't I going to get the natural log? Actually, let me do this. Can I? Yeah, anyway, when I integrate this, I'm going to get the following. Minus natural log of C delta V sub S minus Q equals R C.
T.
Oh, I made a mistake here. This is 1 over RC.
So it's T over RC?
Yeah. And let me move the minus sign from here to here. What am I missing? I'm missing a constant of integration. I'll call it K. Because I have a C there, I don't want to put a C there.
Yeah.
Okay. The next thing I'm going to do is exponentiate both sides.
So take everything e to the power.
Yeah. E to the K. What's e to the K? Just another constant.
Yeah.
And I know in math class, I'm supposed to give it a different name, so I'll give it a different name. Okay. Because
like
normally I'll just write it as K, but people object to that because it's just a constant. We'll figure out what it is. So let me pick a letter.
M.
Okay, M. Okay, let's use M then. So that's a constant. So I'm saying e to the K is equal to M. And I'll determine what that constant is. You will see. We'll see. Okay.
Yeah.
All right. So I have this expression. Let's determine what the constant is. In fact, let me solve for Q. Q is equal to C delta V sub S minus M e to the minus T over RC. Right?
Yeah.
Now, I want to figure out what M is. At T equals 0, what's Q? I mean,
It's
before
just C delta V.
I'm sorry?
It's just C delta V. Or no, -1. Sorry.
No, but I mean,
Minus
before I close the switch, how much charge is on the capacitor?
0, right?
0. So Q is 0.
Oh, okay, yeah.
Okay, so if that's the case, let me plug in T equals 0 there. So then I have 0 equals C delta V sub S minus because e to the 0 is 1, right?
Yeah.
So M is C delta V sub S. So that means Q is C delta V sub S minus C delta V sub S e to the minus T over RC. What is Q after a very long time has passed? When T goes to infinity. When T goes to infinity, what's this term?
Wasn't that infinity?
E to the minus infinity.
Oh, then it would be,
It's 0, right?
yeah.
So this term is 0 after a long time. So let's think about this. After a long time has passed, the capacitor is fully charged, right?
Yeah.
So this is the maximum charge on the capacitor. Right, that's the maximum charge on the capacitor.
Yeah.
So I can say Q equals Q max minus Q max e to the minus T over RC. And so this is the charge on the capacitor as a function of time. what does the graph look like? If I plot a Q as a function of time. Well, it starts at 0, and it increases exponentially up to Q max. That's what the graph looks like. Okay? So we have Q equals Q max or Q max is that. Okay, so far so good. Now, a lot of times we say let tau equals R times C. Because if you look at the units of this, if you look at the units of R times C, an ohm is a volt per amp. And the capacitance is a
volt per
Q
coulomb, right?
over Coulomb.
Or a coulomb per volt. Yeah.
Okay, so
it's a coulomb per amp.
So Coulomb per amp, but an amp is a Coulomb per second. So the units are seconds. So this has units of seconds, and so I'm going to define T as equal to R, tau is R times C, and we call this a time constant. So a lot of times we'll write it this way. And we say, how much charge is on the capacitor after one time constant? Well, after one time constant, that means T equals tau. And so Q is Q max times 1 minus e to the minus 1. E to the minus 1 is about 0.37. 1 minus 0.37 is 0.63. So after one time constant, your capacitor is charged to 63% of its maximum value. You'll hear that terminology. After two time constants, the capacitor is charged about 86%, if I remember correctly, 86% of its maximum value. Okay. So what else can we learn from the circuit now that we know Q is a function of time? Well, we can find the voltage across the capacitor as a function of time, because we know that voltage is Q over C.
Yeah.
And so the voltage across the capacitor is going to be C delta V sub S divided by C. as the capacitor charges up, after a long time has passed, no more current flows because this thing is fully charged. And so the voltage drop across the resistor is 0, and the voltage drop across the capacitor is equal to the power supply voltage.
Yeah.
What is the current in my circuit? Well, I is dq over dt. So I take the derivative of this with respect to time. Okay, so if I take the derivative of this with respect to time, I'm going to get what? Remember, Q max is C delta V sub S. So the current decays exponentially with time. The current's maximum at t equals 0, and as after a long time has passed, the current goes to 0. So if you plotted I versus as a function of time, it looks like that. It decays exponentially. It's not a good exponential. Now the voltage across the resistor can be determined two ways. Oops. That's a C, the voltage across the capacitor. The voltage across the resistor can be determined two ways. And I should say the voltage drop across the resistor. I always make that mistake. Can be determined by taking the power supply, the potential difference across the power supply, minus the potential difference across the capacitor. So if you take delta V sub S minus this expression, you will get the potential difference across the resistor. Or you can take this equation and multiply by R. They're easy to figure out. Once you know this equation, everything else is easy to figure out. So on the exam, I'm not going to have you derive that equation. You're going to need to understand really when that equation is used and when that isn't. If you look at the homework, you don't always need to use this equation. The only time you need to know this equation is if you need to know T or you need to know Q after some time has passed. That is the only time you need to use that equation. And what happens either in the homework, on the exam, I'll give a problem, and they right away want to go to this equation. But you might not need it. You only need this if you need Q at a given T, or you need T if you're given Q. Okay? Does that make sense?
Yeah.
And really, a lot of these problems, you have to understand Kirchhoff's laws, that the voltage drop across this is equal to the voltage drop across these two.
Yeah.
And people forget that. They want to go straight to the equations. And I tend to test people, make sure they understand the concepts. And so make sure you understand that you don't always need to use this equation. It's important to know, but you don't always need to use it. Because really, if like I said before, unless you need to know T, or you need to know Q at some time T, you really don't need to use it otherwise. Use your basic principles. Okay. So this delta V sub S over R is basically the maximum current in your circuit. So we can call this I max. Once you know this, you can figure everything out very easily. just from knowing Kirchhoff's laws and Ohm's law. And also knowing that I is dq dt. After one time constant, the current is 37% of its maximum value.
Jacob asked, how would we apply that equation with two resistors in parallel and two capacitors in parallel?
If you had two resistors in parallel and two capacitors in parallel, good question.
Yeah.
In fact, there's a homework problem like that. So I'm going to erase the board. So this is a good question. R1, R2, C1, C2. First thing, I'm going to reduce these two into a single resistor. So, I have RC circuit, right? I go to this equation. This is C1 plus C2. This is the equivalent resistance, equivalent resistance of the two resistors in parallel. Then Q and of course, you know what this is, right? You can figure that out. That's all you need to do. And then you know the voltage drop across this is the same as the voltage drop across each one of these two. You know that the voltage drop across this one is the same as the voltage drop across these two. So you can just figure out everything in this circuit and then go back to this. That make sense? And you can also figure out the current through each one of those resistors. Right, you can actually find the current through each one of these resistors as a function of time because you know that current through each one of these resistors is delta V over R.
He says, what about the separate voltages between the resistors and capacitors?
The separate, well, they're going to be the same as this, right? They're in parallel. Isn't that true? Whatever the resistor voltage is here is going to be the voltage across either one of those two because they're in parallel. Whatever the voltage,
but they're in series.
Oh, when you're talking about when
the resistors and capacitors are in series.
Oh, okay. I'm sorry. Let me redraw that. Let me. So we're doing a different problem now. Can I erase this then?
What does that equation say on the left? Right.
Oh, this is the equivalent resistance of these two.
Oh, yeah.
So you wanted me to do them all in series.
I think he's saying that the R equivalent and the C1 plus C2 are in series now.
Yeah, they are. Right, now I have a simple RC circuit.
Jacob, I think that's just what we went over before, where instead of just using R and C, we're using R equivalent and C1 plus C2 for the C.
Yeah, that's it. But you're now saying, what if all these four are in series? Are you asking this question?
No,
Oh,
uh,
okay.
because you reduce the resistors in parallel down and the capacitors in parallel. So now you've got the equivalent resistance and the equivalent capacitance in series with each other.
Okay.
So I was wondering about the separate voltages between those two.
The separate voltages across this one?
Yes. And then, well, that one in particular for this problem, yeah.
Well, you just got to divide by delta V sub C. You just divide by C1 over C2. That's it. And then the voltage drop across the resistor then is going to be given by this expression, where R is R equivalent and C is the C equivalent. What I've done, I've reduced this circuit down into a regular RC circuit. And I know that whatever the voltage is across this has got to be the voltage across either one of these two capacitors because they're in parallel.
Okay.
Same thing for the resistor. Whatever the voltage is across this one, I have the same voltage across these two. Because they're in parallel.
Mm-hmm.
Are we okay?
Yeah, I think so.
Okay. So this is the graph I was showing you before. I drew on the board. The charge in the capacitor is a function of time. And then the voltage, the shape of the graph for voltage is going to be exactly the same because the voltage is just the charge divided by the capacitance. So dividing by a number is not going to give you it's not going to change the shape. And then this is the current as a function of time. Okay, I want to show you what the I want to show you live what it looks like as a function of time. So let me. I set up a circuit for you folks. And I'm going to change the view. Let me show you what I have. I have a signal generator. I have a resistor. This is a resistor box. You'll be using these later on the semester. You're going to use this later on the semester when the labs are in person. You're going to use these two. So this is a resistor box. This is a capacitance box. And this device is called an oscilloscope. For an engineer, especially an electrical engineer, this is the most important tool to learn how to use. It's much more important than the multimeter. Because with this, you can look at voltages as a function of time. So you have a lab coming up where you're going to learn how to use this. And then Tyler's in the process of making a video showing you how to use these particular devices. And then what you're going to do is you're going to come to campus and you're going to be tested on it. You're just going to go through a series of measurements with this thing. It's actually easier than the multimeter quiz. But you're going to do it in person. You don't have to make a video. So Tyler or I will test you. Okay? So I'm going to, I cannot do an RC circuit with a voltage that's constant because it's boring. And so I have a signal generator that turns the voltage on and off. It's called a square wave. And I'm going to apply a voltage to my circuit. And what you see here, Hold on a second. I want to have you look at the voltage from the power supply. This is the voltage from the power supply, and the voltage turns on and off. Okay, with these dials, I can change what my display looks like. The vertical axis is the voltage. The horizontal axis represents time. So I actually can measure how much time it takes for the capacitor to charge up. Okay, so the horizontal axis is time, and I have this time base. Each centimeter will represent a certain amount of time. So as I change the time base, I can actually change the size of this trace. This picture is called a trace of the signal. Okay, so this is what the voltage from the signal generator looks like. And I have a resistor and a capacitor in series. Okay, so when I put it to here, so this shows me the voltage across the capacitor as a function of time. And now I can see both. And I like to show you both because you can compare the two. Notice that with my value of R and C, the capacitor doesn't really charge up to its maximum value. And the reason why is because the signal is changing. The voltage is changing too fast. If I make the voltage change more slowly, you'll see that the capacitor has more time to charge up, and it goes to the maximum value. Do you see that?
Yeah.
So I'm really changing how fast the signal changes. And so now I'm giving the capacitor more time to charge up, and that's what happens. Okay, let me go back to my 1000. Now, I can also change the capacitor. If I make the capacitance bigger, R times C is bigger. If my time constant is bigger, I'm making it so that it's going to take longer to charge the capacitor. So if I make my time constant bigger, the capacitor will require more time to charge up, and so that's why it's not charging up to the maximum value. If I make, hold on a second, my capacitance smaller, I'm making RC smaller, and so the capacitance will require less time to charge up. Watch what happens when I make the capacitor bigger. Notice it's not charging up as quickly. Okay, this is where I started. No, that's where I started from. Okay, so by changing the capacitor, if I make the capacitor smaller, then my time constant, RC, is smaller, and then the capacitor will require less time to charge up. If I make C bigger, then R times C is bigger, and then the capacitor requires more time to charge up. Does that make sense?
Yeah.
And so you can see that. Watch, I'm going to make the capacitance bigger, and as I make the capacitance bigger, it's not charging up as much. It's really not charging up at all. What I can do to compensate for that is make the signal a lot slower. So later on this semester, you are actually going to do the lab where you actually test this theory. Okay? In order for you to do the lab, you have to know how to use this first. Okay, so that's why we're doing this. So you're going to do this lab later on. This is essentially the circuit you'll be using. Okay? Although we'll give you certain values for R and C, but this is the equipment you'll be using for the lab, and you're just going to take measurements off this. But it shows you how the capacitance affects the circuit. I can also change the resistance too, because if I increase the resistance, I'm increasing the RC time constant. Questions on this?
I think we're good.
Good? Okay. So I think what I'm going to do is you pretty much have all the material you need to solve most of the problems. The only other problem, I have a long one I'm going to do. Last, but let me show you where we're at right now. I have a problem where we're going to look at the energy stored in a capacitor in an RC circuit, and then I'm going to talk about discharge. In fact, let me do this. Let me talk about discharging capacitor, because this is pretty easy. So I'm going to talk about energy next time, and then I'm going to talk about this long problem, okay? But before I go, let me talk about discharging the capacitor. This won't take long. Suppose I have that circuit. So let me draw this circuit. And I'm not going to go through and solve the differential equation again. In fact, it's an easier differential equation to solve. But so let's say I have a battery, a switch, capacitor here, I don't like where I put R1, but that's okay. We'll live with that. That was really bad placement for my R1. So let me close this switch. And what happens? Well, the capacitor.
The capacitor starts to charge, right?
Yeah, the capacitor charges up. Let's wait a long time. Capacitor is fully charged. Let me open the switch, and then let's close this one. Now what happens? This is a fully charged capacitor. I did this with the light bulb and the 1 farad capacitor, by the way, the other day. If I open this switch, I basically take away the power supply. This thing is fully charged. I have a closed path, and what's going to happen is electrons are going to start to flow in this circuit. The capacitor will discharge. If this side's positive and this side's negative, the capacitor will discharge. And it will discharge until all the energy is dissipated because of the resistors. So I have to apply Kirchhoff's voltage rule to solve this circuit. I just have a capacitor and I have a resistor in series. So this is pretty easy. So I have minus Q over C plus I times R equals 0. But what's I? I is dq over dt. Actually, I is minus dq over dt because the capacitor is discharging. The current that's being produced is because dq dt is less than 0. And so I have minus Q over C minus R times dQ over dt equals 0. And you can show that Q is equal to Q max e to the minus t over RC. By solving this equation, you can show that Q is Q max e to the minus t over RC. So the capacitor is discharging. This is discharging the capacitor. Then I is minus dq, and I forgot the minus sign there. I is minus dq over dt. And that's going to be equal to Q max over RC e to the minus t over RC. I have a minus sign mistake in my notes. So this is the equation for a capacitor that is discharging. This is the equation for a capacitor that's charging up. So the demo I did with the little light bulb and that 1 farad capacitor, that's this example. In that particular example, R times C was huge because it was a 1 farad capacitor. So it took a long time for the capacitor to discharge. Okay. Again, the minus sign means that the capacitor is discharging. Okay, so I wanted to add that in. And so next time I'm just going to do 2 examples and I'll be done with the unit. Okay?
All right.
So we will see you on either Thursday or Friday. Take care, everybody.
Thanks, Professor.
Sure.